we're going to be looking at memory and pointers now. Now that we've covered strings, character strings, and I just want to sort of advise you in advance before we get going. First of all, it's going to bounce around a little bit because I still can't quite figure out the exact right path to make sure that everyone you follow along, and because there's a whole lot of things we all cover at once. Sort of, there's a convergence of ideas here. I'll also say that after we do these 3 or 4 lectures, I get caught up to the pandemic lectures I had from the spring. So, in worst case scenarios, I might be able to use those again. If I do reuse those lectures and you hear something that doesn't match with what we've talked about this term, that's because it was from last spring. But I probably will be re-recording a lot of these. So let's just get going, because what the heck. So we're going to be looking at memory, and this first lecture is going to be predominantly a review of what we've sort of already covered. Probably not well, probably too fast, but review of things we've covered. And then we're going to move on to what that actually means, and then how this relates to pointers and arrays. So we're going to see memory structures, how things are stored, and I want you to be able to be familiar with creating dynamic arrays. And hopefully we'll get to that point today, but that might be another lecture. So here is the general idea. We can go with one of two different things, but the real concrete idea is, if I'm storing my program and I'm storing data, it's got to be stored somewhere. It has to have an actual address, a location for where my data is stored, whether it's instructions in my program or whether it's the data itself that's being stored. Analogously, the metaphor I like to use here is my street address. So there's a difference between coming to my house and knowing where my house is located. You do not have to, in order to go to my house, and when we get to pointers we'll look at this, in order to get something from me at my house, I could give you my address and you can go to my house and get something. What you're not going to do is pick up my house and move it down the street, right? You're not going to move big giant things around. So if I have a giant array, like arrays we've been dealing with, they don't have to be giant, but let's say I have an array of 200 elements. I'm not going to pick that thing up and move all 200 elements down to my program. What I want to say is, yeah, it's over there. It's at Bob's house. I'm going to give the address where that array is located in memory. That's what a pointer is. It is just the address where this thing is in memory. It's that thing over there. Over there. That's what we're kind of going to be talking about. But first, we got to look at memory itself. Memory, when we're talking about memory, where are things located? How much space does it take up? Because if we don't know how much space it takes up, it also adds another little quirk to this, and that is, I need to know how big this thing is in order to find the right address. I'm going to be able to find the addresses correctly. So, to access an instruction, we have a memory address. We didn't even need to know about this because we gave a name to these memory addresses. That is actually what our variable names have been. It's been just a shorthand for that chunk of data over there at position 46, I'm calling it my var. So every time I say my var, I meant get the data, the bucket of data over at position 46. So this would be, here I have a bunch of addresses, right? This is where stuff is stored in memory. And I could have different content in there. It could have operations. I could have instructions or things I'm going to do in my program. I can also have the data being stored. So if I have something like this, I'm making 3 variables called var1, var2, var3. I'm going to store variable 1 into this position right here. I'm going to store variable 2 into this position right here. I'm going to store variable 3 into this position right here. In fact, every single one of the local variables immediately under main even if I made it down here, if it's in main, boom, they're all put in contiguously right here at the top. And then I'll put in the operation I'm going to do next, the operation I'm going to do next, the operation I'm going to do next, and the operation I'm going to do next. This is my program, stored in memory, in locations in memory. Notice this is a hexadecimal number. This is why when I write hexadecimal numbers, I use the 0x in there, because I'm used to staring at a debugger all day long. So I have an address where variable 1 is stored in space. I don't want to know that. I just want to call it variable 1. I'm not going to remember 003210B0. And if I restart my program again, that number is going to be different. It's going to store somewhere else. I don't want to have to actually know where it's stored. I just want a name for it so I can find it again. So it's essentially a shorthand. It is rather than it's like remembering your names versus memorizing where you're sitting in class. You could always move to a different chair in class, right? And then have to rememorize who's in what chair. What I want to do is remember everyone's name. So your name is better for remembering things. That's your name is better than remembering who is in what chair. But effectively, everyone has to sit in a chair when we actually have co-present classes. So this is the idea that we're playing with right now. By the way, variable 1 has to be stored, look at the storage that we have. It goes from B0 to B4 to B8. We're going to look at this in a second, but that's important. So, actually, we're going to look at it right now. Notice it's incrementing by 4 each time, especially for the first three of these. It's incrementing by 4 each time because that's how big the integer variable is. It's 32 bits. At least in this operating system. It can change depending on your operating system, depending on what year you did your program. When we make all this, and each one of my operations this should be also, that's 4 bytes as well. So 4 bytes, 4 bytes, 4 bytes, 4 bytes, 32 bits each and every time. Hopefully I didn't say 4 bits, 4 bytes. 8 bits make a byte. So 4 times 8, 32. Each one of these things is 4 bytes. Each integer is 4 bytes. Knowing how big an integer is changes how you think everything's going to be stored. So each step, it's continuously in a row. Just here's me storing data. Here's me storing data. Here's an operation. Here's an operation, all the way down. And since it's hexadecimal, I'm going in increments of 4 bytes. We're not dealing with bits anymore because it's a pain in the ass. We're using hexadecimal, and we're doing 4 bytes of data each time. So the number I'm changing, it's going to change from a 0 to a 4 to an 8 to a C to a 0 to 4 to 8 to a C. Okay, hopefully that makes some sense. Second thing to note is that our variables are stored in the exact same way as the operations. That is, again, one of Van Neumann's little tricks. He gave us 2's complement. He gave us a bunch of different things, some not so nice things, but he gave us this, that operations and data can just be put together in the same place. Yes, that was me spitting for no reason. They could be bundled together. And so why not? It doesn't matter. Well, operations and data are one and the same. It's just something stored on the computer. And that's a weird thing for a lot of people. They wanted to separate them out. And he said, oh, why do you need to do that? We don't. So they're all contiguous. But also notice, if I had a 16-bit integer, it would look like this. I could store variable 1, variable 2, one after the other, and it would be going in increments of 2 each time, 16 bits. If my integers were 16 bits. If an integer is 32 bits, I need to take up 2 of those spaces. The amount of space I take up depends on the size of my variable. I will fill up that variable. It will be a certain size. A character, our smallest size, is 1 byte. I cannot do a half a byte. I cannot do 1.5 bytes. I will do multiples of, increments of in terms of bytes, but an integer, for our case at least now, is 32 bits, or 4 bytes, every single integer. If I do a short, it's 16 bits, or 2 bytes. So the same amount of space, I can store 2 shorts in the same amount of space that I could use to take up 1 integer. A long takes up twice as much as an integer, so it'll take up 4 shorts worth of space. A character will take up 1 byte, so I could stick 8 different characters into 1 long. But it's all continuous, one after the other. So it's the amount of space these things take up. So here's me storing 2 variables. Here's me storing 4 characters. This is in 32 bits. I can store 2 shorts, and it would be position here, 2, and then 2 bytes later on. So for 2 shorts, I move over 2 bytes, and here's the next short that I'm storing. For characters, it's 1 byte at a time. So it starts at B0, this is B1, this is B2, this is B3. That's how I'm storing my values. Okay, so this is what I just said, so I'm repeating myself a little bit. Because they're only 1 byte in length. And in this case, I could store, like, say, 2 chars and a short, right? They don't have to be the same type. They can be a mixed bag. I can have 2 character variables, and then a short, and then an integer, and then a long, and then a float. And they're just stored one after the other. And again, but you should not get, like, when we're doing this, and I say it's a short, you might know it's 16 bits, but you can't rely on this. You can't rely on where the heck this is going to be stored. It's not going to be consistent each time. There's no point trying to write down where the address is. Next time you run your compiler, you compile your code and run it again, it's going to be in a different address. The big and also you can't assume the size of an integer. You should check the size of the integer each and every time. It can change depending on the operating system. But the big takeaway is there's a link between the variables, operations, and where you find them. And that's the big thing that we're going to be doing. And also, just when you compile it, how the program is executed is just going through one instruction at a time. So when I make a variable, like my variable, very original name, I will put it somewhere in space. And what we're going to get to very, very soon is if I put an ampersand in front of it, I get the location of where that variable is. Rather than, that variable's located over there, my variable is the shorthand for where this thing is located. I can say, I want the location where that thing is located. And I can actually get that in C and C++. I can't get that in Java, but that is a pointer, and I can get that in C. And an int, by the way, again, is not clearly defined for a specific length. Depending on your compiler, it's going to be different sizes. So we need the size of operation, and we'll look at this in a second. But the size of operation allows you to say, what's the size of an integer? And it says 4 bytes. Great. If I run it on a different system and I say, what's the size of it? And it says, let's say, number of years from, let's go back to the 1980s. I say, what's the size of an integer? Maybe 80s or 90s. Say, what's the size of an integer? It says 2 bytes now. Still an integer, but it's half the size as it is now. That's fine. The size of operation covers that scenario. When I change my compiler, I change my operating systems, still works. So we'll look at this. So here is me. Darn it. I have a typo in here. This is print F. I thought I got all of those. I had to refactor all of this to get the cout statements. So hence the typo in here. If I check the set length of a short, or I can pass in an actual short, either the actual data or just the variable type, right? What's the size of a short? It's 2. What's the size of a long? It's 4. What's the size of a long? It's 8. What's the size of an integer? It's 4. In fact, the word int is actually a signed long integer. We don't write it, we just write the word int. Now, this doesn't come up that often, except where we're going to see it everywhere very, very soon. So for the most part, in other languages, you can just sort of ignore the size of these things, but not right now. As soon as we get to dynamic arrays, we're going to need the size of all these things, because C in its infinite wisdom is really old school, and we'll see this in action. We need this size of operation. We need to know how big these things are, because now we need to worry about where memory is allocated, how we find things, how we move things around. So again, if I have a character, it is 1 byte. If I have a 16-bit integer, it is 16 bits or 2 bytes. If I have an unsigned 16-bit integer, it's the same thing. Signed or unsigned does not change anything about our numbers at all, really. The binary is exactly the same in all those cases. And I could store the value 64 in a char, or I could store the value 64 in a 32-bit integer. And the binary is going to be almost exactly the same, except for this one's going to have, this 32-bit integer is going to have a whole lot of zeros in the front. That's really the difference. I like to say, we're going to use the most significant bit as a sign bit. We're not really. It's a shorthand for saying, hey, look, if you got a 1 over here, you know it's a negative. If you got a 1 here, you know it's a negative. But it's not really a sign bit. We've already talked about this. We're doing 2's complement. So I flip the bits and add 1, which we talked about. Hopefully, if you need a refresher on that, I'm more than happy to give one. So if I have a negative 1, this thing is going to be all 1s. Flip the bits, add 1. Right? Okay. How about doubles and floats? Well, again, they're storing a certain size. A float is 32 bits, or 4 bytes. A double is double that. But that's the only consistency we have. Floats could be different sizes, doubles could be different sizes, but a double is always twice the size of a float. So a float is 32 bits right now, and we have a sign bit, a plus or minus sign bit. We have, I think this is the exponent, and this is the actual value we're storing here, but I always mix it up in my head. You don't ever have to look at the nitty-gritty details of a float or a double. You just need to know it's 32 bits or 64 bits. It has a different encoding than integers, and it gets a little wonky because the math is not going to be dead on. You cannot represent the number 0.1 properly with a floating point number. Yes, I said that right. 0.1 cannot be represented as a floating point number just because of how binary arithmetic works. Much the same way as 1/3 cannot be represented in decimal, right? You get this repeating number. 0.1 gives you a repeating number as well. But now that we've talked about this, we've reviewed what's being stored, how big these things are. This is 32, should be 32 bits. Right? It's the same size as the 32-bit integer over here. Okay, so this is a float. Static arrays we've also looked at. So this is just all reviewing things again, but making sure we're on the same page here. So I can make an array called mynums of size 4. I can leave off this 4 and just use this. I could leave on the 4 and leave off this, or I can declare it in a variety of different ways. But this would make this instance right here is going to make an array of size 4 with these 4 parameters automatically set in 5, 7, -1, and 2. So 5, 7, -1, and 2. I chose some random bunch of characters to represent an address in space. That's just the address in space where these numbers are being stored. They're all stored contiguously together. That's what an array does. Okay. Notice something weird going on here. If I want to find out where the 7 is, what could I do? I could take whatever this address is and add 4 to it. There are a bunch of integers, right? So it's 4 bytes separating them. If I took this random address and add 4, what do I get? I get the address for where the 7 is. If I take this random address and add 8, I get this address over here. If I add 12, I'll get this address over here. That's the reason why we count from 0 in computer science. When we're in programming in general, we count from 0 because if I take this address and add 0, what do I get? I get the first element. If I take this address and add 1, I get one integer's worth of numbers, so 4 bytes. I get this address. If I add 2 times the size of an integer, I get this one. If I add 3 times the size of an integer, I get this position. The math is easier to deal with if I count from 0 because the first element is at position 0, position 1, position 2, position 3. That's why we do it. So in case you were wondering why the hell we were doing, using zeros everywhere, that's the reason. Okay. But the problem with our static arrays is once I make this static array of size 4, if I need that static array to be size 5, too bad. If I need the static array to read in a file from outside, too bad. I don't know what I need there. So here is the little problem that we're going to have. If I don't know how big this is, The only workaround I have is to make something colossally large, just ridiculously large, just in case I need all that extra space. So I could do static arrays everywhere, and so I'm going to read in a file, and I'm going to read in all the students in the class, and I need to make the size of my student array 400,000, right? Or maybe 1,000, but still way bigger than the size of my class is ever going to be, just in case I have a large class one year. That's really just a waste of space. I'm going to use up all of this space, 4,000, let's say, 4,000 spaces, and I'm only going to use, let's say, 100, maybe only 80. It's a ridiculous waste of space. And it's just not a very elegant solution. Maybe I don't even need that. Maybe I only need the array in certain circumstances. Maybe on sabbatical one year, oh wait, I'm still making an array of 4,000 elements just in case I needed it. So we need something else, something that can change the size of our array depending on our program. This is what's known as a dynamic array. We're going to get to this. So, but we'll get to it soon enough. So what does this all mean, by the way? So with our base types, we get a lot of different numbers. And if I need to get individual elements, or I need to deal with just a large number of individual elements, I sort of don't want to be passing around this variable and that variable and this variable and copy this variable. It gets really out of hand really quickly. What I want to be able to do, and especially if I'm talking about my program, I pass in some variables, but I need to pass back out a bunch of variables. Well, I either need to pass out a struct with a whole bunch of variables in it, or I need to do something else. Maybe I want to modify a bunch of different variables at once, and now I need a function for changing this variable, and a function for changing that variable, and a function for changing that variable. What we're going to do soon is we're going to use pointers, and pointers allow us sort of a backdoor way of changing variables. It also allows us to deal with arrays, and that's where we're really going to pick things up. So we're going to get to dynamic arrays right about now. Okay, so we're going to hit dynamic arrays. Now I'm going to take a brief pause in the video, and then we're going to look at dynamic arrays. That was just an overview of what we do with sizes of memory. Now we're going to look at dynamic arrays. So hold on for 2 seconds.